Welcome back, everyone. In this video, I'll begin going over the lecture for the volumes of revolution section. Now, to start off, what we're going to do is just look at volume and just very generally describe it. So you know how to find the volume of a few things. You probably have formulas for it. So the volume of a cylinder, you have a height and a radius, and its volume is pi r squared times h. You might know the volume of a sphere, which is 4 over 3 pi r cubed. So r is the radius again. And we can get to non-circular type of objects. We know the volume of a box or a rectangular prism is the length times the width times the height. And there are certainly other ones. So we've seen cones in this class. You can do pyramids, basically anything that's three-dimensional. The volume is asking how much space is this taking up? How much space, how much room is it taking up in a place, in a room, wherever you are. But we're not talking about just the surface, but of course the inside as well. Right? So in general, finding the volume of a generic shape requires a little more calculus than we know. These are special because we know formulas for them and they can be derived without calculus. If you have a very generic type of shape, then in general, you need multivariable calculus. And typically, if you're thinking about that in terms of a specific class, that is calculus 3. However, if we do just take our regular something like y equals f of x and revolve it around an axis, or in general a line, you can actually make a three-dimensional shape and find the volume using just definite integrals. Right. So the idea is we're going to take regions, so things that we pretty much were doing last section to find the area of, but instead of finding the area, what we're going to do is we're going to rotate a region around an axis. So in this visual, I'm taking this R here and rotating it around the x-axis. And so that's why I have these arrows here. So basically what you're thinking about doing is you're taking this box and you rotate it around so it swings all the way around, and what it does at each little section is it makes a little circle. So if you follow just this point here and you watch it rotate around the x-axis, since it's above the x-axis, when we rotate it actually comes in front. So it's going to be in front of the x-axis until we rotate it 180 degrees. So it's exactly halfway down, and then it'll start coming back up, but it will come back up and it'll be behind the x-axis when it comes back up. So it makes a circle. And if you do it with sort of a length here, so not just a point, but a length, you get a cylinder. Now, in general, you don't have to have just a line, so this doesn't have to be just a box, and your shape can change quite a bit. But the idea is you always get these circles. So what I have here, I found this little website that Wolfram Alpha made a slight demonstration on. They have this region at some curve here, and they want to rotate it. Now, in order to actually visualize this, because it's coming in front and behind, you actually need a third axis to draw in. We don't necessarily need to draw that in, but that's why it says Z here. They drew in the Z axis. But what happens is, at least with this little toolbar, is if you bring this down so theta goes up, all it's saying here is that the angle increases. It takes a couple seconds to load, but then this is about a quarter of the way down, and you can see the surface being made here. And we made almost a quarter, so it's gone down about 90 degrees. If I go down to where it's about halfway, maybe about right there, what you'll see is we'll get the front half of the entire surface that it's going to make. And you can tell just based on this little section here. It's pretty much, it starts here and it goes all the way directly below it. And then if I go down to here, this will be about 3/4, so it'll fill up a little more back here. Maybe go around right there. And then if we go all the way down, what it's doing here is it's just rotating it all the way around so it'll complete the surface. Right? And this one looks like a very strange shape. It sort of looks like a pot with a hole in the middle, maybe some weird vase or pot shape with a little circle in the middle. But the idea is no matter what your region looks like, no matter what line you're rotating about, you're always going to get this sort of shape. Every single one of these is a circle. Now, as far as this specific example goes, when you have a straight line, you actually get just a cylinder because you get these circles with height basically. And what happens here is that if this is, let's say, the length of this is delta x. So we know we use delta to represent change in. So this is a change in the x. Then because the area of a circle here, which is what each one of these are, is pi r squared, and I'm calling this r. Right, so just realize that the circle here, the radius is r. Then what we have is, oh, I guess I should explain slightly more because it starts at y equals 0 and goes up to y equals r. Then the volume of this cylinder is, let's go ahead and say here, v equals, well, it's pi r squared because the volume of a cylinder is pi r squared times the height, but the height is delta x. And the idea is for this one, since it's completely flat, what we can do is just do the whole thing at once, and it's actually just a cylinder. And this is how you can get back the volume of a cylinder. So it matches up. So if delta x equals h minus 0, so if we took the entire thing, then what we get back is exactly the cylinder shape and its volume, v equals pi r squared h. But the idea is that especially this part of the formula is going to be important because when we have a not straight shape, so this one's curved, we're of course going to do the same thing we do every time. We use approximating rectangles to draw in the area, and then we rotate that in. And then the height of each cylinder is going to be that delta x. Right, so I'm going to go ahead and just redraw. I have this redrawn, and now I'm going to talk about this a little more generally. So let's say we have a function here, f of x, and we want to approximate the volume of the entire section when it's rotated about the x-axis. And what's happening here is that as we do with the other approximations, we do a left or right endpoint. So I can break the a to b up into, let's say, n intervals. And I choose either left or right endpoints. We know it doesn't matter. But the idea here is whichever endpoint you choose, let's say this one, this is our r. And what you can do, notice here is the r value. If this is like xi, our r value is f of xi, because it's just the y value of f of x at that point minus 0. So r equals f of xi. And then the height is just our delta x, or our b minus a over n. So whatever I chose here, the delta x equals b minus a over n. Right, so that means the volume, since it's still a cylinder, it's just going to be a small cylinder. The volume here of just this little section is pi times r squared, but r is f of xi, times the delta x, which is b minus a over n. And we know from the past Riemann sums that if we want to actually get this exact volume, we take the limit as n goes to infinity. So we get infinitely many of these tiny cylinders, add them all together, and that becomes our rectangle. Or sorry, not our rectangle, our volume. So the volume of R, the region R rotated about the x-axis, is given by v equals the integral from a to b. So we start at x equals a, go to x equals b. Instead of just f of x, we have pi. We're just pretty much going to take this pi times f of x squared. And then we know from past experience that this b minus a over n, this is what goes away when you, and becomes the dx inside here. All right, so this b minus a over n is the same thing as delta x, and when you do the Riemann sum, the delta x becomes dx. So the volume formula of this volume of revolution is pi times f of x squared dx. All right, now this seems like a pretty specific example because we said we have f of x, it's being rotated specifically about the x-axis. You can rotate about the x or y axis. You just have to slightly adjust your formula based on what the rectangles look like, and we'll go through examples like this. But the main thing here is that the f of x is really representing the radius. Because some people, when they write this formula down, instead of using f of x, they actually just use a radius notation as well. So you might see it like v equals the integral from a to b of pi times r of x squared dx. It means exactly the same thing. It just represents the radius more specifically. And you can use either one as long as you understand that f of x really means the radius. So it's the same sort of formula. Now, when you are posed with figuring out the volume of a solid of revolution, which is exactly what these are, there's two possibilities you have to look for based on what the region R looks like. So pretty much the most important thing to distinguish this is when you graph them, you don't really want to graph and visualize the entire solid of revolution. That's very hard to do. All you want to do is graph the region and see where it is in comparison to your axis of revolution. And what we're really looking for here is when the area you are revolving around a particular line is touching the line of revolution for the entire domain, you implement what is called the disk method. And this is really also the same picture we had in the previous examples that I showed above, just explaining this. So it really looks like it's the only example at this point. We'll see the other type in the future. But what I'm describing here is that this is our region R, which is what is being revolved. And it's being revolved around the x-axis, but I just labeled it as the axis of revolution. And what I mean by this touching on the entire domain, let's say this is x equals a and x equals b. So we will only care to revolve this region from here. We don't care what happens to the right of b, to the left of a, only here. Well, on the entire domain is just between the x values of a and b. And you'll notice that the region R is actually touching the axis of revolution for the entirety of the domain. So R is touching the axis of revolution for the entire domain. Now, if it only touches it at like a point, it doesn't even have to touch it at all. Or if maybe it only touches it half the time, then you have to do a slightly different method, which we'll see, but it's built on the same formula. It's not really going to be any more complicated. So this is what we call the disk method. And the main reason is because when you revolve these kind of things, you get just circles or, filled in circles, so disks. And I'll go ahead and show you a slight picture of that. Naturally, most things can just be animated or drawn up in a computer to make it a little bit easier to see than mine. So I just Googled disk method picture here to show you what it really represents. And what you have, they actually have a specific formula. So this is y equals e to the x on the top. And up there rotating it around the x-axis. But the point is, if you draw one of the circles around, you actually get a filled in circle called a disk. Now, that's going to be different than when we aren't touching the entirety of the axis of revolution. So what will happen in those cases is your shape will be a little bit different. It won't be just a solid filled in circle. There's going to be some missing stuff. And we use a slightly different wording to represent that. Right. But what you want to do when you do any sort of volume of revolution problems is draw or at least visualize your region along with the axis of revolution, and then determine this first thing. Is the region touching the entirety of the line of revolution on its domain? And just like before, what I really tried to emphasize in the previous section and on a lot of these sections is that, yes, it's nice to know how to graph these things, and you should. So we should know how to graph y equals x plus 1. That's a line with slope 1 and intercept 1. We should know how to graph y equals 0 because that's a horizontal line. We should know how to graph x equals 0 and x equals 2 because those are vertical lines. But we don't really want to spend time graphing because sometimes these problems are going to give you equations that you might know the generic shape, but you can't graph at least at a reasonable speed. So let's go ahead and just visualize what this looks like. Right, so we want to find the volume of solid obtained by rotating the region bounded by all this stuff around the x-axis. Let's go ahead and type in the equations. Y equals x plus 1. We have y equals 0, which is just the x-axis. So we got these two lines so far. We have x equals 0, and we have x equals 2. Right. Now, when you do it in here, most calculators, graphing calculators, can't graph vertical lines because it's not a function, but luckily Desmos can do all of that stuff for us. So you can clearly see this is the region, and I'll go ahead and just zoom in, but it's the only region that's really stuck inside all four. So we're just right here. And we're revolving around the x-axis. So this is the x-axis, and we're revolving around this. Notice that our region here is touching the x-axis the entire time. And that's important. That tells us we're going to have to use our disk method. But that's just the formula we already have. So the disk method, the formula is the one we derived at the beginning, and we're going to use it. I'm going to go ahead and sketch the picture, but just a very rough sketch because we've already seen it. So let's go ahead. Here's our x and y axis. And I'm not going to be super precise here. This is our y equals x plus 1. The x-axis is the same thing as y equals 0. And then x equals 0 is the y-axis. And then x equals 2. Let's say 2 is right here. That is the other vertical line. So our region R is right here that we want to revolve. And then the axis of revolution is the x-axis, as we are told. But the point here is we have to use the disk method. And you can also draw a generic shape here. So if you grab just a little tiny sliver, a little rectangle here to revolve, what's going to happen is that because it's touching the entire time, we're going to get that same picture I showed you from when I just Googled a picture. You're going to get a really, really tiny cylinder. It's going to be completely filled in though. So everything is just filled in between because there's nothing stopping us. It's not like we're just revolving a little piece right here, maybe just like the top half of this. And then when we revolve it, it would just sort of be like half of this filled in and the middle part would not be being used. So we can see we use the disk method. But this is my preference of trying to think about it is it the region touching the axis of revolution for our entire domain that we are looking at the region? And it is. Okay, so since we have the disk method, that means the volume is the integral from a to b of pi times f of x or r of x, whichever one you want to use, squared dx. The main thing to remember is that this is just the area of the circle that you get when you revolve. And then we're adding up all these area of the circles to get the total volume. That's really what's going on here. Well, what are we integrating? Well, since we're going across the x-axis, our a and b are the x numbers here. So a is 0, where we start, and b is 2, where we end. Let's go ahead and plug that in. Oops, and I should actually plug it in. So a is 0, b is 2, pi is just pi. Now the radius r is just our function, because if I go ahead and look at r here, r is really the length of this, and the length of this is f of x, or x plus 1, minus, and then the bottom one. And the bottom one is y equals 0. So it's top minus bottom. And we can kind of see why that would make sense. If we were revolving around, let's say y equals 1, so it was higher up here, then what would happen is that the radius wouldn't be this long. It would start up here and we would have, okay, the top equation is x plus 1 and the bottom one is 1. So the length of that would be x plus 1 minus 1. But because we can simplify this, you don't want to plug it in like this. It's just x plus 1 because minus here does nothing. So that's going to be our r of x. And that's all you have to figure out. We only need a, b, and r of x in this formula. The pi and the dx are standard. Pi is just a number. Dx is our differential. So we have x plus 1 squared dx. And now all you have to do is integrate this. We got pi. You can take the pi out. 0 to 2. X plus 1 squared dx. Now we have two options here. We can FOIL this out or use substitution because it's not just x squared, which means we should make a substitution. We can't directly just do this, or you can square it out. But it's probably better to use substitution method just to practice it, because if this was cubed or even just a fraction power like 3/2, there is no other way. You couldn't multiply it out. And then if the power is bigger or negative, you can't really do anything either. So let's do u equals x plus 1, and then du equals dx. So that's easy enough. We already actually are solved for dx, which means we won't have to change that or adjust it at all. We have the integral. Now remember, these bounds are starting off at x, and it's always up to you whether you would like to switch the bounds into u bounds or figure out your antiderivative and then plug back in the formula for u. I'm going to go ahead and switch them this time because I think it's a good thing to practice and force yourself to do a little bit. All right, so when x equals 0, our bottom bound, our u is 0 plus 1, which is 1. And when x equals 2, our top bound, u equals 2 plus 1, because that's what x is 2 and u is x plus 1, and that is 3. So our new bounds are u equals 1 and u equals 3. We have the pi outside, and then we're only integrating now u squared, and dx luckily is just du, so we didn't have to adjust solving that at all. And everything here is in terms of u, so we can pretty much just forget that x existed and just go from here. We got pi times, and when we integrate u squared, we get u cubed over 3. Evaluation bar from 1 to 3. I'm going to drop the u just because I know it's already u, and I'm plugging in for u. We get pi, and then I'm going to make a parentheses here. Just remember from the last couple of sections, we started doing this where we just left the numbers out. In fact, we can take out the pi over 3, and we just have u cubed. So we got 3 cubed minus 1 cubed. So we take out the pi over 3, and we only have to plug in 3 and 1 to just u cubed, so it looks like this. We have pi over 3, and 3 cubed is 27, minus 1 cubed, which is 1, and that's 26. So we get 26 over 3 pi. So what's happening here is this shape, you can sort of see that the circles will be getting bigger and bigger. It's actually, because this is a line that's not a horizontal line, but it is a line. It's actually part of a cone, but it's not a complete cone. It would have to go all the way back here and come to a point. So our volume of revolution here, the base is sort of this circle back here where it starts, where it's smallest. So it's just a section of a cone. But what we do is we figured out that the section of that cone, that's volume, is 26 over 3 pi. All right, now I'm going to stop here, and then the next video we'll continue this section.